About the type of rearrangement in which 1,2 shiftings take place, and after Fabry-Sky rearrangement, next rearrangement is benzylic rearrangement, in which there is formation of benzylic by the benzophenone in presence of few amounts of base and in presence of acid, and this reaction is known as Baeyer-Villiger rearrangement, and this reaction is discovered by Liebig in 1838, and this reaction has more and more importance because by this reaction we can form alpha hydroxy carboxylic acid, and or in benzylic acid if we prepare this compound by a benzophenone, and on the formation of benzylic acid in this compound, this rearrangement is known as benzylic rearrangement. So if we take a little look about the benzylic rearrangement, then we have a benzylic rearrangement. Here our substrate is simple benzophenone, and when we treated with base as well as in few amount of acid, there is a formation of product like this, and this compound is known as benzylic acid, and this compound is known as benzophenone product, and reactant is little bit different from the pinacol-pinacolone rearrangement. And here we're talking about the mechanism of this reaction. Then the first step, if our this is our substrate, then in first step OH attack on this carbon, and there is shifted up for this bond to this oxygen, and formation of product like this COC here. Since this bond shifted on oxygen, therefore formation of negative charge, and here there is addition of OH, and this one is pH. Yes, is a phenyl group, and in next step there is a shifting up for this lone pair or minus charge in between this carbon and oxygen, and therefore formation of a double bond, and therefore the valency of carbon is 5 years. Then this phenyl group is shifted to this carbon, and again the valency of this carbon is 5 due to insertion of or shifting of this phenyl to this carbon. Therefore this pi bond is shifted on the oxygen, and formation of an intermediate like this O minus. Here we have a pH, C double bond O, and this one is OH, and it absorbs a proton from the reagent and form product like this. OH, it will be here, OH, pH, COOH, 0 alpha, that is alpha hydroxy carboxylic acid, or this compound is also known as benzylic acid. Therefore this reaction or this rearrangement is a very good example of 1,2 shifting. Here if carbon is taken as 1 and 2, therefore this product is formed by 1,2 shift, 1,2 phenyl shift of 1,2 phenyl shift in this compound, and the formation of this benzylic acid by the rearrangement reaction. Now, the next rearrangement is also very important rearrangement, and this rearrangement is known as this arrangement is known as Baeyer-Villiger rearrangement, discovered by Baeyer and V. Villiger in 1889, and this reaction is a revolution in organic chemistry because formation of so many compounds by this reaction having more and more medicinal use, as well as a constituent of so many perfumes like L-giosamine, and some little bit compound is formed as medicine which is used in the treatment of Parkinson's disease, and some other compounds having high medicinal value. So in this reaction, what happened when a ketone is treated with the peracid, then there is formation of ester via the rearrangement or by the 1-2 shift of a particular moiety or group, and formation of an ester via this compound, and this reaction is known as Baeyer-Villiger reaction. So in simple language, if you can say that when a ketone is treated with perbenzoic acid or peracid, then there is formation of ester, and this reaction is known as Baeyer-Villiger rearrangement. And like this, Baeyer-Villiger rearrangement, in which if we treated a ketone with peracid like peracid, the acid may be metachloroperbenzoic acid, simple peracetic acid like this, CH3COOH, trifluoroperacetic acid, simple H2O2 in some cases, and some other acids are also reported for this case. Then there is formation of product like this, O and here O, like this group is known as ester group. That is the formation of ester via this reaction, and this reaction is very important. And if you take some other example, then there is a ring expansion is also found in this reaction. And if we take another example like this, here we have a cyclohexanone, like this is a ketonic group, and it treated with metachloroperbenzoic acid. There is formation of product like this. The oxygen is inserted here, and there is formation of product like this. It is also ester. That is, the oxygen of this metachloroperbenzoic acid is inserted in between this carbon, and formation of ester like this. And similar reaction will be happen if we take another reactive intermediate like this, then the product is also like that. Here the ring is size 1, 2, 3, 4, 5, 6, 7. Here 1, 2, 3, 4, 5, 6, 7. So there is a ring expansion in this reaction. Here if we take per acid, then we know that the structure of per acid is like this. So any group is here like MEPH or any R or pH. So this oxygen is also behaves like nucleophile, and this lone pair is also behaves as nucleophile and having capacity to attack on this carbon because this is partially negative, this is partially positive, and formation of product like this. Then both have a similar reaction in which in one product there is insertion of oxygen, however in another there is an insertion of CH2 group. Therefore the reaction is very important. So if we consider, if we look mechanism of this reaction, then we find that if we take an example of this reaction via mechanism, then if it is treated with OH, OCO, here we take CF3. Okay, then in first step there is attack of this lone pair like nucleophile, because we know that if a lone pair attack on the carbon, then known as nucleophile, and it abstract the proton, then it known as base. Therefore here this lone pair attack on this carbon, and therefore shifting of this bond here, and formation of product like this, O minus, like that. Here O, since this lone pair is utilized in one formation, therefore H, and here positive charge, here O, here CO, and another is CF3, trifluoroperoxylic acid. And in next step, this proton is shifted here or abstracted by this negatively charged, and therefore the product like the intermediate of this reaction is like that. It will be shifted here, and it will be shifted goes to here, and there is a formation of compound like this. And in next step, to get this lone pair is shifted here, and this bond is shifted here, and this bond is shifted here. Here the reaction is take place not because removal of this leaving group, because of weakness of this oxygen-oxygen bond. So the drastic force or the force behind this reaction is the weakening of this OO bond than the efficiency of this leaving group. Therefore this product is formed. Then our next product is like that, O, H. Here, since this positive charge shifted here, there is a creation of positive charge here, and formation of double bond, and this is O, like that, and since this bond is shifted to here, therefore this goes to here, and formation of this bond is break, therefore O minus CO and CF3, and this one is product. And in next step, this hydrogen goes to here. This hydrogen is absorbed by this compound and a formation of simple product like this. In this step, we have a case like O positive double bond and this one. Like this one. 7-membered, and this bond is shifted here, and the formation of O double bond, this one, O here like this. This is an ester site, ester, plus this one CF3 COOH. So this is a simple reaction in which formation of ester is take place, and the mechanism behind this is somewhat very important. And we take another example in which we can see that how if we have two different groups that are shifted on the oxygen, then we can see in another example, if we have a case like that, O and CS3, if it treated with metaperchlorobenzoic acid, there are two cases here. In first, the oxygen inserted in between this, and in second, the oxygen inserted in between this. Then the first product is like that, OCOCS3, and second compound is like that, OCS3. That is, in this reaction we see that this phenyl group is shifted, or this phenyl group is shifted, and the formation of product like this, and in this there is shifting of methyl group, and therefore the formation of this. If we take if we nomenclate here first and second, then we find that in first case here there is formation of 90%, and here is 0%. That is, if we have example like if we have methyl, if we have ethyl, isopropyl, we have tertiary butyl, then 90%. Next product is this one, then 87%, and next product is called 33% and 2%, and here it is 0, here 6, here near about 67, and here near about 77%, like it equivalent to the phenyl group. So in this reaction, what happens that the product formation is increases by increasing the capacity or tendency of groups in this reaction. So this reaction shows that if we have a group which is stabilized in the reaction by a resonance or by another another methodology, then the product formed by those reactant or by those intermediate are more and more. However, the groups which are not able to stabilize more and more in this reaction, uh, and then they form the product in lesser amount in comparison to those groups. Therefore, the ratio selectivity of this reaction is very important, and we can form product which we want in this reaction in and also predicted the nature of compound, which one will be major in this reaction and which will be minor in this reaction. So this reaction has more and more importance. If we take another example like this, if we have a bicyclic compound like this, if tertiary butyl type compound, and fulfill the condition of this one, therefore we see that this is like that. We see that if we treat it with meta or chlorobenzoic acid, there are two chances here. There are two possibility. First one is that inserted of oxygen here, or second one is here. Since here after insertion there is formation of secondary carbocation, however here is formation of primary carbocation. Therefore the possibility of insertion of oxygen in between these is more in comparison to this. Therefore the product formed in this reaction is like this one. Here we have a example, we have like that, and here O and C, and like that, O and that, and the product is this. Okay. So this is the reaction by which we can prepare so many compounds. If you take another example of like we have a cyclopentadiene, and it treated with a compound like this one, C double bond C, Cl, Cl. Here 2 plus 2 cycloaddition reaction is take place in first reaction, and there is formation of product like this. Like this, and if this treated with zinc, removal of this group and formation of product this one, like this, like this. Here 2 hydrogens outside the plane are also present, and double bond is here. And when it treated with the metachloroperbenzoic acid, then we find a compound like this, M metachloroperbenzoic acid. Then we find the compound like that. C, here there is insertion of O, here CO, here like that, here and like that, here 2 hydrogen, and this product is formed by a simple cycloaddition. Somewhat we seen pericyclic reactions on how this reaction can occur. What is the HOMO, highest occupied molecular orbital, LUMO, lowest occupied molecular orbital, LUMO, lowest unoccupied molecular orbital. HUMO, highest unoccupied molecular orbital, somewhat like energy, and these are the energy levels of this compound, somewhat sigma, pi, sigma, pi, sigma, star, and this such type of reaction is seen in the some pericyclic reactions or photochemical reaction which are initiated either by thermal or photochemically, and that is the another cases or another examples of the organic reaction which are also more and more important, in which Diels-Alder, retro Diels-Alder and another type of reactions can be easily explained, and the formation of product can be seen. So this compound is known as jasmino, and used in L-jasmino and used in perfume. So if we consider the stereochemistry of this reaction, then if we take an ketone with a chiral compound with a chiral carbon, then the product formed is not fully racemic, because like SN2, inversion is not take place in this reaction. Retention is observed more and more, and retained product is more than 90%, and this is due to the bond formation or due to sigma of HOMO of that particular chiral carbon, and sigma of LUMO or sigma star of LUMO of oxygen per benzoic acid, in which there is shifting of sigma HOMO to sigma star LUMO, and via same phase. Therefore inversion is not take place like SN2, because in SN2 there is inversion is formed due to there is inversion in structure is found is due to there is bond formation by sigma anti-bonding, that is LUMO to sigma bonding HOMO orbitals. Therefore inversion is take place in SN2. However, in this reaction inversion is found in very lesser amount. Therefore in this reaction, retention of the product if we take an chiral carbon in this compound. Similarly, there is possibility to formation of product by shifting of another groups. If we have a bulkier groups, if we two groups, like first one is smaller and another is bulkier, like 1 degree and 2 degree, then 2 degree is shifted oxygen in more easily in comparison to 1, because in transition state 2 degree secondary carbon form more stable transition state. However 1 degree is less stable. Therefore that secondary moiety is shifted to oxygen is very easy, and the corresponding product is formed in this reaction.